I want to show you some tricks that are used in integration. And we can call that, if you like, integration like a statistician or summing like a statistician. And the trick involves simply recognizing the integrals or the sums as sums which we've already seen. So let's take a short example, take two examples as a matter of fact, and let's start with addition, summation. So we're going to take a Poisson example. We have a random variable x, which has a Poisson distribution. And what that means is that the mass function for the random variable is given by this expression, e2 minus lambda to the power x over x factorial for positive integers and 0. Now, we already know that this sums to 1. It's obviously always positive. And we know it sums to 1 because this is just a rewrite of the Taylor expansion for the exponential function. So to begin with a simple example, let's suppose we want to compute the expected value of x. Now, for a discrete variable, this is simply the sum over all possible x's of the value of x times p of x times the probability mass function at the point x. Now, p of x is only positive at the integers we mentioned earlier. So this sum, although it's written as a sum over all real numbers, it's really only a sum over the over x from 0 to infinity. So let's rewrite this a little bit. And we can start by noting that the first term in the sum is actually 0. So if x is 0, then this is 0. So the whole quantity is 0. So this is really just the sum where x goes from 1 to infinity, x times e2 minus lambda to the power x over x factorial. And we can now rewrite this, take e2 minus lambda out. No, well, actually, we don't need to do that. So we can cancel one of the x's, e2 minus lambda to the x power still over x minus 1 factorial. Since x factorial is just x times x minus 1 and so forth, we cancel one of the x's. This still goes from 1 to infinity. And notice that if we hadn't removed the 0, then we would have had to worry a little bit here because there is no such thing as minus 1 factorial. So we would have had to think about that. Now, we can now take one of these lambdas outside the sum. We still have x from 1 to infinity, still have e2 minus lambda. We now have lambda to the power x minus 1 divided by x factorial. And notice, sorry, divided by x minus 1 factorial. And now notice that we can now replace these x's, and you can do that either by saying, well, let's do this properly, y is equal to x minus 1. And then this is the sum, e2 minus lambda to the power y divided by y factorial. And y, as x goes from 1 to infinity, y will go from 0 to infinity. And this is exactly the sum we started with. We know this sum, it adds to 1. So this whole thing is simply equal to lambda. So what we've shown is that the expected value of a Poisson variable is equal to lambda without doing any actual sums. All we did was recognize the sum, a sum. And to show you a slightly more powerful case, suppose we want to compute e to the power, the expected value of e to the power x, where x is Poisson. Then again, this is the sum over all x's, e to the power x times p of x. And now this is an expression like this. And again, let's rewrite this. Now, notice here that we have e to the power x. And then we also have a lambda to the power x over here. So product of two things to the power x is just we can just multiply the two together. So we have e to the power x and lambda to the x. So that's e times lambda to the power x. Again, divided by x factorial. And the sum goes from 0 to infinity. Now, suppose we take this e to the minus lambda outside. So we have e to the minus lambda here equals e to the minus lambda. Now, we're almost back to the original probabilities, right? Remember the original probabilities, they were e to the minus lambda, lambda to the power x divided by x factorial, except here we have e times lambda to the power x. So to get something similar, we need to replace lambda in this expression by e to e lambda. So in other words, what we're missing here is we're missing an e to the power minus e lambda here. And to not change anything, we multiply by plus e to the power e lambda outside. So now this is equal. We just multiplied by a weird 1, if you like. And now we know that this thing adds to 1. So we're left with e to the power e lambda times e to the power minus lambda. So this is equal to e to the power lambda times e minus 1, which is really a rather neat result. And if you think about this a little bit, you will see that if we hadn't done some rewriting like this, we would have either resorted to a Taylor series variable substitution, etc. But the trick here is in realizing that we just get something which adds to 1.